Hello, this is Philip Myers from PEMY Consulting. Welcome to the second unit on engineering units for the plant engineer. In this unit, we work with Newton's law F equals ma. It's essential to understand this to understand units. There's more than meets the eye for F equals ma. Actually, it derives from Newton's universal law of gravitation, which says that the force between two objects is some constant g, big G, times the first mass times the second mass divided by the distance between them squared. Masses are idealized as point masses. So on Earth, m1 would be the mass of Earth, r would be the distance from the center of the Earth to the surface. This formula becomes ma, and so g m1 over r squared should be acceleration. Wikipedia states that g is 6.67 times 10 to the minus 11 meter cubed per kilogram per second squared. Note that I've used exponent notation to write this all on one line. First, let's examine the units of g in the universal law of gravity. So we have this expression g m1 m2 over r squared. We know that the m cubed over kilogram per second squared comes from Wikipedia. That's the constant. But now we have to multiply it by mass squared over distance squared, or kilogram squared per meter squared. You can see that the units will cancel out. If you cross out the kilogram squared with a kilogram in the bottom, you get kilograms here. Then if you do the same for the meters cubed divided by meters squared, you get meters, and the seconds is unchanged. So you get kilograms meters per second squared. That's a Newton. So that check is good. Next, let's determine the units of the red symbols, which should be A. So we take the same units for G and multiply by meters or kilograms per meter squared. Kilograms per meter squared works out, if you cancel out the units, meters per second squared. So that's acceleration, so that checks. But you don't need to know all this. You just need to be firmly remembering F equals ma. A good exercise is do this all over from memory using exponential notation. Here we are going to examine G sub C, A, and G in more detail. The two formulas to know are F equals ma. That's the generalized second law of Newton. It works anywhere in the universe. But for Earth, we use W equals mg, where W is weight, which is a force, is equal to the mass times the gravitational constant. In the USCS, this is 32.2 feet per second squared. G sub C, the conversion factor we talked about before, it's 1.0 in coherent systems, but it's not 1.0 for the USCS. So often you will see F equals mg over G sub C, where this is the 32.2 conversion factor. Again, as I said earlier, you don't need it. It's harder to remember how to use it than it is just to know what the basic conversion factors are and apply them appropriately. Another issue you might have is why not write this W equals ma? These equations, even though they have identical units, they are not the same. In particular, A is acceleration. It's how fast an object is changing its velocity. Here, G is the gravitational field strength. It is not acceleration. And to prove that, just consider yourself standing on the ground, not moving. You're not accelerating yet. Your weight still is equal to W equals m, your mass, times the gravitational constant. So just be aware of that point. They're handled pretty much the same in practice, though. G you can think of as just a proportionality factor between weight and mass. So here are a few conversion factors. G in the SI system, that's the standard gravitational constant, is 9.81 meters per second squared. 1 Newton is equal to 1 kilogram meter per second squared. We'll talk about this later. These are dimensions, so mass times length over time squared is what these units are. G sub c is a ratio of 1, which gives you the conversion factor. So it's kilogram meters per Newton second squared. That's and 1 over G sub c would be the reciprocal of that, but you could write that as newtons per kilogram meter per second squared. So you can see that it's taking a newton, dividing it by exactly the same thing, which is a kilogram meter per second squared, so its value is 1. And it's used as a conversion factor. But again, it's hard to remember that. If you remember a newton is a kilogram meter per second squared, you're going to be just fine. Here are two other conversions. The pound mass, you look these up typically on the internet, is a 0.45 kilogram, or a kilogram is 2.2 pounds mass. Here's an example. We have a 125 kilogram mass. We want to know its weight in newtons and in pounds force. Well, the appropriate equation would be W equals mg. So we have m, 125 kilograms, times g, which is 9.81 meters per second squared. We know that that is 1226.25 kilogram meter per second squared. We multiply out the units. This is to be converted to newtons, so we would take that conversion factor of newtons per kilogram per meter per second squared, and you'll end up with newtons. Again, this seems overkill. You don't need to remember all this. You just have to know that 1 kilogram meter per second squared is a newton, so you can substitute that directly in for this quantity. To find the force in pounds, we'll just use the conversion factor that was shown previously. That's 4.5 newtons per pound force. So I have to have pounds force in the numerator, so I know that I have to divide by the 4.5 newtons per pound force. You can see it here, 4.5 newtons. If I bring the pound force here as in the bottom, then I have the conversion factor of 1 that I need, and I can cross out the newtons here, and I end up with 275.51 pounds. So 1 pound is per 4.5 newtons is 1.0. As I said, it's the same idea as 12 inches per foot is 1.0. It doesn't change the value of the measurement, the actual physical measurement. The formal definition for a newton is shown with the 3 bars, and it means 1 newton is 1 kilogram per meter per second squared. Here's a note on accuracy that we talked about earlier. If I were to do this with 6 or 7 digits that I get from the internet, I get 275.577928 pounds mass, and when I convert it, I get 275.5775. So even this calculation is off at the 4th digit. It's 4 parts per 10,000 between row 5 and 7. Here you can see that we have 275.5 pounds of force, but that's going to be off a little bit depending on how many digits you use in the conversion factors. If you really need high accuracy, then it takes a lot of specialized effort and research to make sure that you have units of the appropriate digits. In engineering practice, we don't typically need that. Here are some convenient conversions for the pound force. G is 32.2 or 32.174 feet per second squared. It's probably adequate just to remember 32.2. Again, you can use G sub c, but I recommend it because this is looking kind of complicated, and you've got to remember whether it's G sub c or 1 over G sub c. So when you see the mg over G sub c, the conversion is taking 32.174 pound mass feet per second squared and per pound of force, so it's making that conversion. Again, you don't need to use G sub C. You can just put the units in and let them cancel out appropriately. 1 pound force is 32.2 pound mass feet per second squared. This is the unit that you should remember. When you look up values on the internet to make conversions, you'll find things like 1 pound mass is 0.45 kilograms and 1 kilogram is 2.2 pound mass. Here is an example. A part has a mass of 191 pound mass. What is its weight on Earth? So the formula or conversion that you need is to remember that 1 pound force is 32.174 pound mass feet per second squared. You don't even have to remember this because you know that F equals m, pounds mass, times A, feet per second squared. You do have to know that in the USCS you have to carry this 32 along with it. So in our calculation we have W equals mg, 191 pounds mass, times this conversion factor or acceleration, and we end up with 6145 pound mass feet per second squared. Now, using the conversion factor formally, which you won't have to do after you get a little familiarity with this, you can divide out these units and they'll end up as pounds force. So we get 191 pounds force. This shows that in the USCS a pound mass has the same magnitude, the 191, as pounds force, but they are different things. A pound force has pound mass feet per second squared units, whereas a pound mass is a mass unit. The second part of the problem is a part weighs 500 pounds on Earth. What is its mass? So we just take mass equals W divided by G from this formula. Take the 500 divided by the gravitational acceleration, and we get this value, which has pound force second squared per foot squared. So here, to convert it to mass, we have to multiply 32.174 because we need this pound force to cancel. We're trying to get pounds mass, so we take the reciprocal of the conversion factor. These will cancel out and you end up with 500 pounds mass. So again, the numerical value 500 is equal in pounds mass is equal to the numerical value of force in pounds force. But remember, they're not the same thing. The units are different. I'll just quickly run through the slug, although it's kind of a obsolete system. It actually makes more sense than the USCS. G is the acceleration on Earth. Remember that a pound force has to be a mass unit times feet per second squared. Well, if you choose a slug as the mass unit, then G sub C is slug feet per pound force second squared. And the conversion factor would be pound force per slug feet per second squared. So 1 pound force is 1 slug feet per second squared. It's the slug of mass whereby if you apply a 1 pound force, it will accelerate 32.2 feet per second squared. So this would be a coherent system of units. Here's a quick example. An object weighs 10 slugs. How much does it weigh in pounds force? W equals mg. 10 times the acceleration is 321.74 slug feet per second squared. But we know that 1 pound force is the same as 1 slug feet per second squared, so when you cancel these units, you end up with 321.74 pounds of force. What are the takeaways from this module? Weight is a force in a gravitational field on Earth. Next time we'll look at standards for units, dimensions, and conversions. The things to remember is these conversion factors: 32.174 pounds mass feet per pound force second squared. If you commit this to memory, then you don't need all of the formulas. You can just use this or its reciprocal to cancel out the appropriate units. This is, the reciprocal of this could be just flipped over, but I'm writing it as pounds force per 32.174 pounds mass feet per second squared. This, of course, is the definition of a pound force. So it's really pound force over pound force, which is 1, which is what you want when you do these conversions. So F is pounds force equals MA, which has to have this 32.174 factor in it, times pound mass feet per second squared. Thank you.